In this video, we're going to talk about error bound. Okay, so the question really is, how good is our approximation? The whole point of making a Taylor or Maclaurin series is to approximate a function so you can find values and derivatives and integrals of functions you might not otherwise be able to work with, at least by hand. Of course, with graphing calculators, it's easier to do these things without needing Taylor series. But the point is, we create a polynomial that looks like the function and behaves like the function to a certain point, of course, depending on the interval of convergence. Well, once we've used this polynomial, we want to ask, how good is our approximation? Anytime you approximate, you should be asking how good. So our two methods of approximation are the alternating series approximation, or error bound, and what's called the Lagrange error bound. And these things both give error bounds, okay, where they say, we're not going to be more than a certain value away. So I wrote this. It says both methods give a small number such that, well, we hope that our approximation is within a certain margin of error of the true value of the function. So this is our Taylor approximation, and we say, well, we hope we're within, we get a bound. Let's say it's 1/100th. We hope we're within 1/100th below or above of the real function's value. Another way to say it is that the Taylor approximation is within this interval, either 1/100th below or 1/100th above. I just said 1/100th to kind of give an example. But the question then becomes, how do we calculate our error bound? Like I said, there are two methods, the alternating series or Lagrange. We're going to do an example of both. So first, we're going to find the first two non-zero terms of Maclaurin series for sine. So hopefully you know that. If not, you could certainly look back, but the first two terms are just this, okay? So if I'm going to estimate the sine of 0.2, I'm going to plug 0.2 in. I'm going to have 0.2 minus 0.2 cubed over 3 factorial, and I get 0.199. It's 0.1986, repeating like that, but rounding to 3 decimals. Now the question is, how good is this series? How good is this approximation? Well, if you can remember from when we did alternating series before, the way you do an alternating series is simply by finding the next term. Okay, so if you add up two, if you use two terms, the third term would give the error bound. If you used 10 terms, the 11th term would give the error bound. Well, the next term in my sine, my Maclaurin series for sine, remember it's x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. So my next term is this. So my next term is x to the 5th over 5 factorial. Well, now I simply plug 2 into that, right? I've already plugged it into the series, so I plug 0.2 in. When I do that, I get 2.67 times 10 to the negative 6th. This is my error bound. So alternating series are really nice because all you need to do is calculate the next term, or the first term you didn't put or calculate in your series. And what, again, that tells me is that I am within, my estimate is within this of the true sum. Or of the true value, I guess, in this case. Okay. Now that's, again, this is a bound. I might be even closer than that, but I'm not more than 2.67 times 10 to the negative 6th away. Now this is pretty impressive because I only use two terms. To already be within 0.00000267, with two terms, this is really, really a powerful series for approximating. So anytime you have an alternating series, all you need to do is find the next term. Let's look at when it's not alternating. So something like e to the x, and again I said find the third degree Taylor polynomial for x cubed at x equals 0, or e to the x. So this is a Maclaurin series. So again, we have done e before. I'm going to just write it out. If you don't remember how to generate it, I would urge you to go back and either do it or look at a video of how to do it, but I'm going to do it for the sake of time like that. Okay, there's our third degree polynomial. So estimating f of 0.2, we plug that 0.2 in. And I get 1.221. Now, this is not an alternating series, right? This just keeps growing. But Lagrange error bound still relies on the next term in the series to an extent, okay? So I want you to look at this, and this formula looks very, very difficult, but it actually isn't a bad idea. It says that you won't be further away, than the maximum value of the next derivative evaluated at x, and x minus a to the n plus 1 over n plus 1 factorial. So here's this kind of boiled down, okay? You're still going to find the next term. For us, that next term would be x to the 4th over 4 factorial. You're still going to do that, okay? You are going to plug 0.2 in to that. You're going to have 0.2 to the 4th over 4 factorial. But we have a multiplier that we have to put out front. It has to do with the maximum of a derivative. Okay, and I want to come back to that for 1 second, or in a second. I just wanted to explain one other thing. You see this x minus a here. The x minus a has to do with the fact that we may not have centered our series at 0. So you may have, your series could have been about the point x equals 2, and then you'd maybe be estimating 2.2. So you'd have 2.2 minus 2. So this really represents your distance, the distance from where your series was created to where you're trying to estimate. Now for us it was 0.2 because we created a series about x equals 0 and we're estimating about 0.2. But if you created a series about 2 and we're doing 2.5, then it would be 0.5 to the 4th. So it's pretty easy to evaluate that, but I just want to point that out. And this bottom n plus 1 factorial just has to do with the fact that we're going to the next term. So the maximum value of the next derivative. Well, this is what makes the Lagrange error bound a little bit more difficult than alternating series, because in alternating all you need to do is find the next term. But in Lagrange you need a maximum value of your derivative, and really between where you made the series and where you're estimating the series. So for us, from 0 to 0.2. Now here's the thing. This value is really an estimate. And it's an estimate because if you knew what it was, if you knew what the maximum value of the derivative was, then why wouldn't you be able to just calculate e to the 0.2, right? Why wouldn't you be able to just do that? So this is an estimate, of course. All the derivatives of e are e. So that makes this easy, because essentially we're just maximizing e to the x on the interval from 0 to 0.2. Well, we know what e to the x looks like, right? We know what that looks like. We know it's increasing, so we know e to the 0.2 is the maximum value of e to the x. But again, why would we know that? Otherwise, we wouldn't be estimating e to the 0.2 if we knew it. So we create an estimate. Here's what I'm going to do. I'm going to use 3. And you say, well, why would you pick 3? Well, here's the easy answer. E to the first is about 2.71. So why not just say it's about 3? And you'd say, yeah, but you were estimating from 0 to 0.2. E isn't even close to that. It's not even close to 3 from 0 to 0.2. So what? This is an error bound. What I'm creating here is something that says I'm not possibly more than this away. Go big. This doesn't have to be a real fine-tuned approximation. You want to estimate big. And I did. You're right. It's nowhere near 3 from 0 to 0.2. But that's okay. I just made the largest possible estimate. So if I calculate this, if I actually multiply that out, I 0.002. Okay? And that's the error bound. Now, the actual value of e to the 0.2 approximately is 1.2214. And if I went one more decimal out, this was 3. So you'll see I'm even closer than the error bound said because I'm correct to three decimal places, right? And this said that would be the bound. Remember, the bound says I'm not more than 0.002 away. It's an upper bound. Hopefully your estimate is even closer, and ours was. And that's why we can kind of do this, let's just estimate. Sometimes you do this with trig functions. That's easy because a trig function will never be bigger than 1. Otherwise, you just make a large value that's a multiplier. Okay? On the AP exam, how this is usually asked is it will give you a value or give you a graph that says the derivative isn't more than blank. And then you plug that in for your maximum. Okay? So one more time, an alternating series, you simply find the next term and plug in the value. A non-alternating series, we do the Lagrange error bound. We still find the next term, but then we have a multiplier out front, which is the maximum value of the next derivative. Okay, so the derivative that would go with the next term. This was easy. E to the x, all the derivatives were e, so I just said, well, between 0 and 0.2, the maximum value of e, yeah, it's probably, it is this value, but I went big. I said, I'm just going to multiply it by 3. E is approximately 3, and I'm going to multiply it by 3. That's the hardest part of Lagrange, is picking that number. Don't make that the hardest part. That can be just a straight estimate, and you don't need to work that hard at picking that number. Don't let that be the part of this that is a sticking point.